Welcome to lecture 7.1, the inverse sine, cosine, and tangent functions. Our objectives for today are to define the inverse sine function, find the value of an inverse sine function, define the inverse cosine function, find the value of an inverse cosine function, define the tangent function and find the inverse of it, find use properties of inverse functions to find exact values of certain composite functions, find the inverse function of a trig function, and solve equations involving our inverse trig functions. So, just to summarize all of these objectives, what we're looking at is inverses. We've talked about sine, cosine, tangent, and now what we're going to be doing is looking at their inverses, because just like with the mathematical concepts that we've discussed before, they have inverses. Much like multiplying is the inverse of dividing, sine, cosine, and tangent, we will look at their inverses and use them to solve. Okay. So let's start by looking at the exact value of some of these expressions. We're going to start with sine inverse of 1/2. So in order to find the exact value of this inverse function, I'm going to start by just saying that we're looking for a theta where sine inverse is 1/2. So what I'm going to do is I'm going to let my theta equal sine inverse of 1/2. Sine inverse is giving us a theta. So whatever this value is, it's our theta. Usually we have sine of theta, right? Theta is the thing that we're plugging into our sine, but this time it's our inverse. So instead of putting in theta, we're getting out theta. And one thing to note is that we are restricted because we are going to be staying between negative pi over 2 and positive pi over 2. That goes back to what is the domains of these functions. In this case, we're looking at a range because it's the inverse. So we want to stay in a workable area, right? We don't want to look at values that are going to be falling on those asymptotes. So what we're going to do is we're restricting our theta to fall between pi over 2 and negative pi over 2. Now, if we take theta equals sine inverse of 1/2, then we are going to do the inverse, right, of sine, and the inverse of sine is sine inverse. Let me say that a little bit clearer. I see here I have sine inverse. So in order to undo sine inverse, I'm going to take the sine of both sides. So I have sine of theta and sine of sine inverse of 1/2. Sine of sine inverse, those are inverses of each other. So I'm left with sine theta equals 1/2. And remember, we're still between negative pi over 2 and positive pi over 2. So I need to see these values. So what I'm going to do is I'm going to make a table. And really, if you're working through these problems, you can make the table one time and just reference back to it each time. That's what I do. So my table is going to be theta and sine theta. So as I change my theta, what is the sine theta telling me? And I'm going between negative pi over 2 all the way to positive pi over 2. And I'm going to see the values of sine theta because we want where sine theta equals 1/2. So let's start with negative pi over 2, and then negative pi over 3, negative pi over 4, negative pi over 6, 0, pi over 6, pi over 4, pi over 3, pi over 2. So, if theta is negative pi over 2, what is sine of theta? That will give us a negative 1. If theta is negative pi over 3, sine of theta is going to give us a negative root 3 over 2. When theta is negative pi over 4, our sine of theta is negative root 2 over 2. At negative pi over 6, sine is negative 1/2. At 0, sine is 0. At positive pi over 6, sine is 1/2. At pi over 4, sine is root 2 over 2. At pi over 3, sine is root 3 over 2. And at pi over 2, sine is 1. Remember, this is coming from our unit circle. If we follow our sine values around and these different theta points, then we can see what they are. If you need to, pull up your unit circle again. It's an excellent reference to have. And like I said before, our big three, right? Pi over 4, pi over 3, and pi over 6. Those are our big three where we want to know what's happening sines and cosines at these big three. So now we're going to look at what's going on when sine theta is 1/2. Sine theta is 1/2 right here. So we're looking at pi over 6. So my theta is pi over 6. That is the exact value of sine inverse of 1/2. Okay, let's look at another one. Cosine inverse of 1/2. We're going to work this one out very similarly to the last one, except instead of a table filled with sine values, now we're looking at cosine. So I'm going to let theta equal cosine inverse of 1/2. And we are between 0 and pi. No. Okay, 0 and pi. That's all I wanted to do, was make that cleaner. Okay, so since I have cosine inverse of 1/2, what I'm going to do is the inverse of cosine inverse, which is cosine. So I'm going to take the cosine of both sides to get rid of that inverse. I have cosine theta and cosine of cosine inverse, which leaves me with cosine theta equals 1/2. And we're in between 0 and pi. So my table of theta values and cosine thetas will start at 0. Then we'll do pi over 6, pi over 4, pi over 3, pi over 2. Let's do 2 pi over 3, 3 pi over 4, 5 pi over 6, and 1 whole pi. And you can get these values. How do I know what values to use as theta? Reference your unit circle. Pull your unit circle out and see in between 0 and pi, what are all the different radian, the big ones, the radians of theta that I could see and use. Which ones are valuable? And these are the valuable ones that pop out. So, when theta is 0, cosine is 1. When theta is pi over 6, cosine is root 3 over 2. When theta is pi over 4, cosine is root 2 over 2. At pi over 3, cosine is 1/2. At pi over 2, cosine is 0. At 2 pi over 3, cosine's negative 1/2. 3 pi over 4, cosine is negative root 2 over 2. At 5 pi over 6, cosine is negative root 3 over 2. And at pi, cosine is negative 1. What were we looking for? We were looking for where does cosine theta have a value of negative 1? And we see that happening right here. So cosine has a value of 1/2 at pi over 3. So theta equals pi over 3. So the value of cosine inverse of 1/2 is pi over 3. Okay, our last one in this objective is tangent inverse of negative root 3 over 3. So, like we've been doing, let's start by letting theta equal tangent inverse of negative root 3 over 3. And this one falls between negative pi over 2 and positive pi over 2. So now, since we have a tangent inverse, if I want to undo that or think of the inverse of it, it's tangent. So I'm going to take the tangent of both sides. And I have tangent of tangent inverse of negative root 3 over 2. Oh, 3 over 3. Which tangent of tangent inverse is going to leave us with tangent on this side and negative root 3 over 3 on this side. And we're still following the restrictions that were given. So let's get a table going of our thetas and our tangents at these different theta values. So we're going from negative pi over 2 to positive pi over 2. Negative pi over 2, then we'll do negative pi over 3, negative pi over 4, negative pi over 6, 0, and then we'll swap to positive pi over 6, positive pi over 4, pi over 3, pi over 2. Okay. Now the thing about tangent is we notice probably that these ones are not less than or equal to. They're just strictly less than. And why is that happening? Well, if I find the tangent of negative pi over 2, it's going to give me undefined. And so is the value at pi over 2. These values of tangent are undefined. That's where we have the asymptote happening. So let's look at negative pi over 3. At negative pi over 3, our tangent value is negative root 3. At negative pi over 4, tangent is negative 1. At negative pi over 6, tangent is negative root 3 over 3. At 0, tangent is 0. At pi over 6, tangent is root 3 over 3. At pi over 4, tangent is 1. And at pi over 3, tangent is root 3. We are looking at where is our tangent value, negative root 3 over 3. And we find that right here, negative root 3 over 3. So our theta is negative pi over 6. This tells us that tangent inverse of negative root 3 over 3 is negative pi over 6. Okay, so for the next section, what we're going to do is look at how do we use our calculators to figure these things out. So what I want to show you is what it looks like typing it into a calculator. If we have sine inverse of 3 over 5, what we do is we tap our sine inverse button, and then we put 3 divided by 5, and this is going to give us 0.64, just about, and that's all there is to it. 0.64. And this is approximately because we did have to round it off. The next one says cosine inverse of negative 0.357. So same thing, we're going to tap that cosine inverse function. We'll have negative 0.357, which gives us about 1.94. And our third one, tangent inverse, same thing, find your tangent inverse button. Tangent inverse of 8, which gives us about 1.45. Even on your graphing calculator, if you're using a TI-84, you would press the second button and see right above the sine, cosine, and tangent, there's the sine inverse, cosine inverse, and tangent inverse. So just one extra button, you would press second sine, and that'll give you sine inverse. Second cosine would give you cosine inverse, and second tangent would give us tangent inverse. Okay. For our last example, second to last example, we are going to find the exact value without using a calculator. Most often, the calculator will not be able to give us an exact value because it's going to be giving us a never-ending decimal. So if we want something more exact, then we have to do it ourselves. If we're looking at cosine inverse of cosine of 5 pi over 7, for example. Now, remember our domain that we're looking at here, we want our theta to be in between 0 and pi. Now, why are we looking at it this way? There might be a couple reasons. If we look at the cosine function, from 0 to pi is where we see this period. And if we start repeating values again, because the cosine does go on forever, then we could have infinite thetas. In this case, we just want to limit it to that very first period of the cosine, which is why we look at 0 to pi. I want you to really focus on where is this theta, like what is our restriction for each, for sine, cosine, and tangent. That way we can use it when we are solving, especially finding exact values. So if we're looking at 5 pi over 7, 5 pi over 7 is in the interval. It's falling in between 0 and pi. So that allows us to take cosine inverse of cosine of 5 pi over 7 without changing anything. Cosine undoes, cosine inverse undoes cosine. It's the inverse of it, quite literally. So that leaves us with 5 pi over 7. And that's our exact value. We wouldn't put that in a calculator, one, because it told us not to, but also because it's exact, just as it is. We know that pi is never-ending number, so that there's no way that we could calculate this to an exact value without rounding somewhere. So this is our exact value, 5 pi over 7. Next we have sine inverse of sine of 7 pi over 10. Now what is our interval? Our interval is negative pi over 2 to pi over 2. So you might say, okay, well, sine inverse is the inverse of sine, so I'm left with 7 pi over 10. Except 7 pi over 10 is not in the interval. Okay, 7 pi over 10 falls outside of our interval. So what we need to do is reference our unit circle to find out where would we get the same angle in our interval. And if you think about what's happening on a sine graph, you're thinking of, okay, so it has happened, you know, sine looks like this never-ending squiggly line. And, you know, if our interval is looking at some spot, we are focusing on a spot that's outside of it. But we can find that same spot in our interval, and that's what we're going to do. We're going to find that same spot in our interval, so that way we can give an accurate, exact value. So if we look at the unit circle, for example, and we find 7 pi over 10, it's somewhere about here, 7 pi over 10. As always, my unit circle and graphs are not to scale, so please be nice as you look at them. This is 7 pi over 10. Now what we've noticed is, one thing that I notice, for example, is that if I were to see what is this angle that it's making, if I go from the horizontal upward, well, that's just 3 pi over 10, right? So if I wanted to, I could put it in our interval and find it over here. And now that's inside of our interval. So instead of having sine inverse of sine of 7 pi over 10, we're going to rewrite it in our interval, sine inverse of the sine of 3 pi over 10. And we have sine inverse of sine. Those undo each other. They're literal inverses of each other. So we're left with 3 pi over 10. And that's our exact answer. Okay, let's do another one. Tangent inverse of tangent of negative pi over 4. What's our interval? Negative pi over 2 to pi over 2. If we think about, okay, negative pi over 4, well, negative pi over 4 is in our interval. So we don't have to change it. We don't have to find the same angle in our interval. It already is in the interval. So tangent inverse of tangent of negative pi over 4. We have the inverses here, so we're left with negative pi over 4. And we found some exact values. I don't know, I find these pretty fun. I really like finding out about what undoes another operation, which operation undoes another one. So finding and learning about these inverses is always really fun because it's like untying a knot. It's undoing the operations is really nice, I think. Okay, number 4, this one is asking us to find f inverse for this function f. Our function is 2 cosine x plus 1, and then state the domain of both f and f inverse. So f I can write, and I'm going to rewrite, as y, y equals 2 cosine x plus 1. So that way I know where is my y, where is my x. Now if we think about this before I even start, I'm going to actually get one of the domains out of the way and write the domain of this first function. So the domain of f, domain, remember from algebra class, what is all the input values, or what are all the available x's that we can plug into our cosine in this case. Well, cosine, if we think about it, what does cosine look like? It looks like that never-ending squiggly line, so our x values, right? We can plug in any of them. So since that's the case, our domain is negative infinity to positive infinity. It's a nice one. And there's no restrictions on it. Okay, so now let's find the inverse. Let's find f inverse. And the one method that we can do is switch the x and y and then get y alone. So then we want to do our algebra magic to get it back into y equals. So first I'm going to switch x and y to cosine y plus 1. I've swapped them, and now I want to get y all by itself. So I'm going to subtract 1. Whatever I do to one side, I have to do to the other. So I have x minus 1 equals 2 cosine y. And then we'll get cosine alone, so we'll divide it by 2. So we have x plus, x minus 1 over 2 equals cosine y. And what undoes cosine? Well, that would be cosine inverse. So I'm going to take cosine inverse of both sides, which leaves me with y equals cosine inverse of x minus 1 over 2. So we found the inverse. So far, so good. And now we want the domain of our inverse. This one isn't as straightforward as the domain of cosine. What we have to think of is, okay, what was my domain of cosine inverse? What are all the things that this cosine inverse can have? What are its limitations? The cosine inverse, the domain of it, is actually the range of the original cosine. So that might be something you take with you. The domain of cosine is the range of cosine inverse. And the range of cosine is the domain of cosine inverse. So what we know of our cosine, we can apply to our cosine inverse, which gives us tons of information, to be honest. So if we go back to our range of cosine, the range of cosine is from -1 to +1. This will relate to our domain of the inverse. So the domain of the inverse is going to start with a -1 to a +1. But remember, we have a lot of stuff happening inside of our cosine inverse. What do we have happening in there? We have an x minus 1 over 2 happening in there. So what we need to do is we need to find out what values of x are we allowed to plug in so that this stays in between -1 and +1. So now we're going to do algebra, solve for x, but because we're working with inequalities on both sides, we need to do whatever we do to one side, we have to do to the other and the other. So whatever we do in the middle, we have to do on the left and the right. So what do I mean? Well, the first thing I would do is multiply by 2 to get that 2 out of the bottom. So I have to do that on all 3 sections. So now we have -2, we have x minus 1, and we have +2. Okay, the next step to get x alone is going to be to add 1. So I have to do that on all 3 sections. So this is going to leave us with -2 plus 1 is -1. In the middle, we're left with x. And then over here, we have 2 plus 1 is 3. And this is our domain. These are the values that we're allowed to plug into our x, do all these things that are inside of our cosine inverse, and we'll still stay within -1 and +1. So our domain of our inverse function is from -1 to +3. And that's what we wanted. We wanted what is our function, what is our domain of our function, what is our inverse function, and what's our domain of our inverse function. All right, our last example is going to find an exact solution to this equation. -6 times sine inverse of 2x equals 2 pi. Now this one we're going to solve algebraically. So we will have -6 sine inverse of 2x equals 2 pi. And what I want to do first is isolate the trig function, because once I have a trig function with nothing being added to it, nothing being multiplied to it, just that trig function, I can start undoing it with my inverse trig functions. So I have a -6 times that sine inverse, so I'm going to divide that away first. Divide by -6, and whatever I do to one side, I have to do to the other. So I'm left with sine inverse of 2x equals, and we have 2 over -6, which leaves me with -pi/3. Just reducing that fraction. And now that I have sine inverse all by itself, I can undo it. And how do I undo a sine inverse? I use sine. So I'm going to take the sine of both sides. Whatever I do to one side, I have to do to the other. So sine and sine inverse undo each other. I'm left with 2x equals sine of -pi/3. Okay, refer to your unit circle or your memorized knowledge. What is sine at -pi/3? Well, the sine at -pi/3 is a value of -√3/2. And now we want x all by itself. We don't want two x's, so I'm going to divide by 2. And whatever I do to one side, I have to do to the other. So x is going to equal, well, if I have -√3/2 divided by 2, you can turn it into multiplication, flip the second. This gives me -√3/4. So my x value is a -√3/4. And we have solved our equation. It's an exact answer. We didn't have to round anything. So it is complete. As always, it is a good idea to take your x value and plug it right back in and make sure that this side does in fact equal 2 pi. Checking your answer after you find your answer is something I highly recommend, especially in this class and moving forward into your other classes as well.